Thank you very much. So it's a work of my PhD student Meng Hu, who couldn't come here, so I'm giving his talk. And so this subject came from this recent progress in the geometric methods on fluid dynamics. So one recent progress concerns stochastic modeling using geometric methods. And in this effort to insert stochastic effect in fluid dynamics, there are several ways, of course, to do this. But one specific approach is to try to preserve as much as possible the structure of the deterministic equations, like relevant conservations laws, symmetries, Lagrangian and Hamiltonian formulations, etc. Another progress has been about how to discretize the equations for fluid dynamics by trying to do the same kind of things, preserving also the relevant conservation laws, Lagrangian and Hamiltonian formulations. And the question we ask is, how can we extend this structure-preserving approach to the stochastic extensions that have been proposed here? So in this talk, I will concentrate on a tiny portion of this work, which consider the time discretization of the fluid equations. So I will start with some preliminaries and motivations, a bit extension of what I just said. Then I will also review what we mean by variational integrators. And then I will present his result on stochastic Lie group variational integrators. So this is the usual slide to start with for those who are not familiar with geometric mechanics. The idea is that when you start studying a mechanical system, you have usually a configuration manifold and a Lagrangian, and your equations of motion are given by Euler-Lagrange equations. And this simple starting point gives rise to a very clear framework how to study geometrically the system. For instance, if you pass to the Hamiltonian side, if you assume the Lagrangian is non-degenerate, then you get the Hamilton's equations. And the main property of these equations is that its flow is symplectic. It preserves the canonical symplectic form on the phase space. So this is one of the properties I mentioned earlier in the two cases, the stochastic case and the discretized case. This is the basic case. Also, you have, of course, the Poisson formulation associated with canonical symplectic form. Concerning symmetries, if the system has symmetries, which are here implemented by saying that the Lagrangian has these symmetries, then it's easy to see that the momentum, the mechanical momentum in the direction of the symmetry is preserved. So this is the famous Noether theorems that also holds in both situations that I mentioned earlier, in the discretized and the stochastic case. So half a slide about geometric methods for fluid. As I said earlier, we start with a configuration manifold. Here it's for a fluid in a closed container. It's a diffeomorphism group, the diffeomorphism group of the manifold omega or the domain omega, which we can interpret as a Lie group. From this point of view, we can associate variational formulation, Poisson bracket, the usual object, quadrant orbit, Noether theorems, etc. And all this is well understood by implementing the theory of reduction by symmetry in mechanics, which for the easiest case of just one incompressible inviscid fluid, it's just dividing the tangent bundle of your Lie group by the Lie group itself, in which case you get the Lie algebra. So this is the main relation from Lagrangian to Eulerian fluid dynamics, right? You have your Eulerian velocity, which arises as pulling back to the identity the velocity flow of the fluid, right? So recently there has been a proposal how to stochastically perturb the fluid equations while maintaining as much as possible the structures underlying the equation. So if you were there this morning in the fluid session, you have seen one way to do this stochastic perturbation. Here I will mention another way. So this is modeling, so it's not the truth, it's modeling. There are several ways to do this model. And the question we ask here is assuming a stochastic perturbation of this reduction formula here, like this, for instance, how can one derive fluid equations of motion that still preserves as much as possible all what I said earlier, these symmetries, Lagrangian, Hamiltonian formulations, things like this. So a proposal has been given by Daryl Holm in 2015, and the idea is quite consistent with first principle. We add this perturb equation as a constraint in Hamilton's principle. And what you get, I don't show the equations, you get a stochastic Hamiltonian system on the diffeomorphism group with this Hamiltonian. And then it's almost easy to see that all the rest stays intact, right? Symplecticity, reduction by symmetry, and Kelvin circulation theorems, they survive to this stochastic extension. So this is, but for instance, energy conservation is lost, but this is part of the modeling choice, right? Other modeling choice could, for instance, preserve the energy, but maybe destroy Noether theorems, etc. It really depends on what you need. So on the numerical side, in the deterministic case, we know well how to discretize fluid equations using the framework of geometric mechanics. So what is missing is a time integrator on Lie group for this kind of stochastic Hamiltonian system. So this is what I will present now, and this is the result of my student. So just to give you a flavor of what are variational integrators in case you haven't seen them, otherwise you can just wait 2 slides. The idea is to discretize the Hamilton's principle instead of discretize the equation. So there are several ways to get structure preserving integrators, but here I chose the Lagrangian way. And the idea is the following. You have your Hamilton's principle, right, in which you select the critical curve among all possible variations, critical curve for the action functional. Then you decide to discretize this curve in a sequence of points, and what you have to do is to discretize the Lagrangian and then just compute the action functional associated to discretize Lagrangian. And you apply Hamilton's principle and you get the scheme, right? So you will find that I'm repeating myself all the time. Indeed, I'm repeating myself. The result of this kind of scheme is symplectic. In particular, it preserves the volume, the Liouville volume in the phase space. And in addition to that, if the discrete Lagrangian that you choose to start with here has the same symmetries as the original Lagrangian, then there is a discrete Noether theorem. Right? So you can really have the same kind of conservative result that I showed you in the stochastic case and in the deterministic case. Now it's in the discrete in time case, right? And also interesting is that these two main properties of variational integrators can be proven using variational arguments. You don't need to see anything else than this Lagrangian side. So this is the equations that we want to discretize. So first on vector space. So in vector space, stochastic Hamilton's equations have this form, right? This is a form due to bismuth, right? In which you extend the Hamiltonian part by stochastic Hamiltonians. And there is a variational principle associated to this, right? Which is really, in fact, the phase space principle on vector space for Hamiltonian system. So the big difference with deterministic case is the equivalence between these two statements, which doesn't hold in the nice way that we have in the deterministic case. But this equivalence is well understood. For instance, It has been clarified in this paper by Lazaro Cami and Ortega in 2008. How this equivalence doesn't really hold, but still it gives us some insight how to proceed. So the goal is to find some symplectic integrator for these equations. So they are known, right? They have, in fact, if you apply the midpoint rule naively, it turns out that what you get here is a symplectic integrator that converge to the solution of the deterministic of the stochastic continuous equations. So this is some kind of old result, right? That have been derived by hand, right? So when we saw that, we say, okay, so on Lie group, we just replace these terms by doing the same thing on the Lie group. So you multiply by half the step, etc. And in fact, no, it's very hard to imitate what you see this on a Lie group by keeping all the rest intact. I mean, symplecticity and geometry, etc. So the idea was to find a variational derivation of that one, right? And then hope it's easier to generalize the variational derivation from vector space to Lie group. In fact, it will work like that. It's much easier than to try to guess what would this look like on Lie group. So the situation is like this. So this is the variational, the action functional whose critical point condition gives this. So the idea is that it's still the form of a Hamilton phase space principle in discrete form, but we have to insert intermediate configurations. Of course, this is well known that this has to happen, right? When we do, for instance, Runge-Kutta variational integrators, things like this happen. But here it's done in this way, which is a bit different on the Hamiltonian side. So not only this function, discrete action gives us the scheme, but also gives us easy proof of the symplecticity of the scheme. I don't give details, but it's well known in general that if you take you restrict the action to the solution space of your scheme, you take the variations, you get just the endpoint condition like this. The derivative of the action gives you just the end point conditions at the beginning and the end of the trajectories. And this helps you to identify the one forms, right? You take another D, so this is 0, and here you get that the scheme is symplectic, right? Because you take the differential here, this is the discrete flow, so it shows you directly that the flow is symplectic. So just giving the proof of these results from a pure variational argument, right? So how can we now generalize this for systems on Lie group, such as, for instance, these fluid equations that we have seen? So the stochastic Hamilton equation on Lie group, in the trivialized case, they take this form. Here you have the G component, which corresponds to the Q part. You have the mu component, which corresponds to the P part of the Hamilton's equations. This is just to recall the formula. And you have the Hamilton phase space principle on Lie group that takes this form, right? This is nothing else than the trivialized canonical one form. This is your deterministic Hamiltonian. This is the stochastic part driven by the Brownian motion here. So to give you an idea, on SO3 it just gives you the usual rigid body equation augmented with this stochastic momentum associated to the derivative of h with respect to the momentum mu, right? Okay, so now we apply usual procedure when we want to discretize Lie group equations on Lie group. So we use a local diffeomorphism between the neighborhood of 0 in the Lie algebra into the neighborhood of the identity in the Lie group. So this is the main ingredient to build Lie group methods, right? When you want to, for instance, following this paper by Iserles et al., that's the structure preserving way to discretize ODEs on Lie groups. So for our case, SO3, just to illustrate, for instance, we can take the Kelly map. It is indeed a diffeomorphism, a local diffeomorphism from G to G. So now, as I said, it's cumbersome to guess how to write the Lie group version of this, but it's not too cumbersome to write the Lie group version of the discrete action, right? So that's what we did here. And here it's almost immediate, considering the previous work that have been done in the deterministic case. So we each time replace difference in the phase space in the vector space by this combination in the Lie group, in which you multiply on the left the k+1 position by the k+1 twiddle position -1, right? And this is sent back. This is in the Lie group. This is sent back in the Lie algebra, so that you can in fact pair with the momentum mu. Same thing here and here. So here it's just to recall that you not only have the sequence of phase space points, but you also have intermediate point, as it's expected in this kind of methods, right? So now applying the variational principle, we get this critical point condition. So we can, I can describe a little bit this. So this is just the derivative of the Kelly transform, right? This is the coadjuvant operator. This is the momenta mu and mu twiddle. These are the Hamiltonian contribution. Same thing for these equations. And here, if we look a little bit more into these equations, we see that they don't correspond to what I showed you earlier here, strictly speaking. In fact, it's just another reorganization of the equations. That's the explanation, right? Because when you take variations, you get 4 equations, and then you combine them to get these two here, right? So it's hard to see the analogy with what I said on vector space, but this is the true generalization to Lie group. It works. Just you have to change the way of writing the equations. So he could prove that this scheme indeed converge in the mean square sense with global order 1 to the solution of the Hamilton's equations here, these ones, right? Okay. Symplecticity. So without entering into the details, to prove the scheme is symplectic directly can be very cumbersome, but if we use this approach of involving the variational proof of a symplectic of the symplecticity of a scheme, it works easily, and it even gives you the correct expression for the discrete one form, right? For instance, they are given like here, and you can indeed directly get that the scheme is symplectic by doing the same proof as earlier, right? You compute the derivative of the action restricted to the solution of your scheme, and then you look at the endpoint expressed by these one forms. I star is just because I look back this form on the submanifold of solutions. This is the flow. You take one exterior derivative and you get that the discrete flow is symplectic, right? So this is the first structure preserving property, right? Symplecticity. The second one is Noether theorem. So here we assume that, so we are on a Lie group, we assume that the system is invariant under a subgroup, K a subgroup of G. And like here, for instance, since the Hamiltonian has been trivialized, we don't see the action on the second slot, but it's the same thing. So the variational approach gives us what should be the discrete version of the momentum map to be preserved, right? So in the continuous case, it was just add star G minus 1 of mu. And in the discrete case, since we are doing also midpoint rule, the expression is a bit transformed by the discrete process, but this is what we get. Okay, so the final result is the preservation of quadrant orbit, right? Which for the rigid body would correspond to preserving this sphere centered at the origin. And again, this is something that can be directly seen from the scheme if we compute a little bit. Okay, so the rest was just how to explain, how to apply this to the fluid picture, but maybe I can skip this and directly go to the conclusions. And I can, I think, just mention that now we are using these stochastic variational integrators to build a variational in time discretization of this stochastic field equation. So this is what he's currently doing now. Okay, and I stop here. Thank you.
There's that very nice paper by Vadim Arnold in 1966. I know it very well because I was born that year, which is an analogy between Euler equation of rigid body and Euler fluid. Right? So you can derive the both from the second order theorem with loop. And then, if you want to derive variational integration method for rigid body, I think it goes back to the Marsden proof that if you want to preserve energy, momentum, and simplicity, you can do 2 out of 3. You cannot do all 3 together.
Yeah.
So either you choose simplicity, that quadrant orbits are preserved, meaning angular momentum and energy, right? So you have to choose 2.
Yeah.
Here you have a similar situation. You have quadrant orbits, which is a vorticity, which is Coulomb theorem. Yeah. You have energy and you have simplicity.
I don't have energy. I have the symplectic way to preserve energy.
Okay, so you relax this energy conservation.
Yeah. I mean, I'm doing symplectic integrations. I'm not doing anything strange. So the energy is just oscillating.
So energy is not preserved. I mean, it's not in the form.
It's very well behavior.
Yeah.
It's the usual symplectic behavior.
Okay.
Yeah.
Just one comment.
By the way, here I'm not so sad about this because these stochastic things preserve the symplecticity, the Noether theorem, but not the energy.
Yes.
So.
Yes.
Okay.
And the very interesting paper you have had in a fluid session with open container.
Yeah.
Then this reduction symmetry, which goes to the particular labeling, right? Is it also does it hold for open container as well?
Yeah, it does.
It does.
Yeah.
Yeah. Because you
as soon as there is a system that has Lagrangian and Eulerian description, there should be something
you
that
can go back
explains
and forth
this.
Lagrangian.
Yeah, you should.
Yes.
Yeah.
Okay, thanks.
Yeah.
Yes, just a small question. The scheme you propose is explicit or is
implicit?
Implicit.
Yeah.
Okay.
There is a lot of research toward explicit symplectic methods, so it would be nice to see if the stochastic version of this can be done. I have no idea. I never. But it's important.
Thank you.
So when you apply this to the to fluid dynamics, right? So to the infinite dimensional setting, not to after discretization some very high dimensional setting. So you need to apply the KD transform.
Yeah, exactly.
To this very high dimensional setting. Do you approximate the inverse matrices somehow, or do you?
No, I use something a bit harsh, but which works. So in these formulas, um, in many formulas, when we use the Kelly transform, we have this higher order term here. And it turns out that for the case of fluid, if we neglect this term, we don't see any change.
Okay,
So
this
our
is
Kelly
not-
transform turns out to be very nice at the end of the day.
Okay.
For this example, in our case, yeah,
Okay.
yeah.
That's mathematical.
Otherwise, if we keep this for the fluid simulation, no, we never end the computing part.
Okay, sure. Any idea of how to do higher orders? I mean, we just get order 1 due to the stochastic.
Some ideas, but with maybe it's not too useful for the fluid problem, but it would be useful for maybe if we stay rigid body or things like that. But for the fluid problem, it's not helpful, we think, so far, to go higher order in time. This is just.
Question. Do you preserve the Casimir function?
Yeah, we preserve the quadrant orbit. Yeah, we preserve the Casimir function only in the finite dimensional situation. For the fluid, we have the problem that when we do the spatial discretization, we destroy some things behind the Casimir, so we cannot preserve the Casimir for the fluid. But as long as we are doing matrix group like this properly, we preserve the Casimir, which is known in the deterministic case. It's not due to us.
Okay.
One question.
Okay. The
Is
last
it okay?
question. Okay.
So is it correct that the moment map is also perturbed?
The moment map is
The
also
moment map is also perturbed.
is not perturbed by the stochasticity. No. Because it's a geometric object, not related. We change the Hamiltonian. The momentum map
Say that
doesn't
the
see
Hamiltonian
this.
is the moment map.
The
The
Hamiltonian.
one-dimensional case. You have an action of the.
Oh yeah, but this is not the Hamiltonian of the system. It's the Hamiltonian of the symmetry.
Okay.